Hi everyone, welcome to Multimodal Weekly webinar series hosted by the team at 12 Labs. This is our weekly webinars. We've been meeting every single Friday over the past 1 year or so. Some of the topics that we tend to cover include new research in multimodal AI and foundation models. Since we focus a lot on video understanding, we also have folks talk about some of the projects in that domain that I'd like to share. Practitioners talking about interesting multimodal application in different verticals. And finally, internal talk from our team members discussing tutorials and guides using our platform and APIs. In some of the recent session, we have partners talk about enhancing video production media search, where a bunch of researchers talking about the latest work on multimodal, enriching speech and text, touch as modalities, open source model, etc. So for today's session, we actually circle back into industry, and we'll have two startup founder who will share some of the work that they've been doing in this space. The first speaker is going to be Jesse Clark, currently the co-founder and CTO of Marqo AI. And actually, Jesse is a return speaker. He gave a talk last year about Marqo and some of the work that they've been doing in the vector search space. So I'm excited to see some of the change that, at least some progress that the company had been making over the past year. And more specifically, he would talk about a technique called generalized contrastive learning for multimodal retrieval and ranking. And yeah, curious to hear more about the technical details of that work and the implications of that as well. The second speaker is going to be Alexandre Berkovic, currently the CEO and co-founder of a company called Adorno AI, which is doing work in audio, intelligent audio creation. So I got connected with Alex, I think probably 1 or 2 months ago at an event, and I know they've been doing a lot of exciting work to enhance video production, leveraging the audio creation technology that Adorno is building in-house. And we're actually working together on a blog post between 12 Labs and Adorno. So yeah, just excited to see how Alex is going to present the vision that he has for this collaboration. With that, for the attendees, quick logistical note, feel free to send your question on the Zoom chat. And after each speaker finish, we'll have a short Q&A session as well. So the format is that Jesse is going to go first for maybe 20 minutes. We have a short Q&A, and then Alex can come in and cover the second half. And we'll have a short Q&A as well. Yeah, so I will stop sharing my screen. And yeah, Jesse, do you want to go ahead and start your talk? Great, let's see it.
All right, can you hear me? Yep.
Yep.
Cool. Hey everyone, yeah, super excited to be here. My name is Jesse Clark. Like James said, I'm co-founder and CTO of Marqo. I'm going to talk a bit about some of the model details and the model training methods that we've developed for vector search. So it's called Generalized Contrastive Learning for Multimodal Retrieval and Ranking, or sort of how to adapt contrastive learning for search. So I'll talk a bit about some overview of basically of vector search and sort of then how that actually plays into some of the practicalities of model development. Oh, hang on, why can't I? Oh, there we go. Quick about me, I'll keep it quick. Yeah, like I said, co-founder and CTO of Marqo, sort of long history in science and machine learning. Started out in physics and then spent quite a bit of time at Stitch Fix and Amazon doing a variety of sort of projects, particularly around deep learning and machine learning. Like I mentioned, yeah, what I'll talk about, I want to sort of set it up before going into the actual technique and some of the details of that. I sort of want to give a high level overview of what is vector search. I think everyone will be very familiar with this, but it's really important because even though it's relatively sort of simple in practice, it really comes down, essentially to the embedding quality, which is where your model training comes in. And that's sort of what motivates some of the technique development that we have, which is this generalized contrastive learning. And the idea here is that we can actually adapt some of the model training techniques to be much more aligned with a lot of the practical aspects of building these models for actual search in production. And then look at some extensions of this and sort of how do you actually make them more performant, from a production standpoint. So being able to actually, retain the performance of the embeddings, through their sort of relevancy, while also using less resources. So, Matryoshka representation learning and learning to binarize. So, using shorter and smaller vector embeddings and also lower precision vector embeddings. So just to set it up, we'll go over vector search. What is vector search? I think everyone's heard so much about it. The key point here is that queries and documents are represented by vectors. So in traditional keyword search, it's still using the text-based form, but in vector search, you represent everything as vectors. And so this means that you can actually turn anything into a vector, basically that anything can go into a computer. And so this means that you can now search over not just text, but images, video, audio, quite literally anything that you can put into a computer. And the key concept is that you have this proximity in vector space between related concepts. And so now, the semantic sort of similarity is encoded by their distance within this vector space. So things that are co-located together have some meaning. But of course, this meaning comes back from actually how you train the models and how the embeddings and the underlying space is formed. And so, once you have a query in this space, the items that are closest to that query are essentially your search results. So a very simple concept in practice. And here's just an example of that in 2D. We have a query point come in, all the documents are in blue, and you can actually start to calculate the distance between the query point and all these other documents. You get this list, you sort it by the distance, and that's your search results. So, again, very simple in practice, really powerful, but the whole technique essentially relies on having very good representations, because if you don't have good representations, then everything kind of falls apart. So you need to have, this relationship, this sort of, relevance, semantic similarity, whatever you really care about to be encoded in this space, because that means that you can actually get really good results back without having to do a lot of work. So I'll sort of just do a quick tie into how it fits in with Marqo. So we work on sort of end-to-end, vector search engine. And I think the key component here is that, like I mentioned, a lot of it has to do not just with the K&N lookup for vector search, but actually how the models are trained and served. And so the retrieval component is what I think a lot of people are familiar with, but actually to build these sort of production systems, it needs to be much more holistic. So you need to really care about how the models are trained, and then you've obviously got to serve them, because it's the quality of those embeddings that really matters in terms of your search results. And you don't really want to degrade that in a production system. You really want that to be as high quality as you can, because this directly impacts your end-stream business metrics, for example. So a lot of the training methods as well, which I'll talk about, also have an eye on production, so that they're very much focused for, you can train, your objectives can literally be the same as what you do in production, so that there's no skew between your training and test. There's a whole host of different use cases. For vector search, I think people are probably familiar with these. They've come across them in their day-to-day lives. So search and RAG, again, this is sort of the canonical use case where you type in a query, you get back documents, maybe it's text documents, maybe it's products. This also then leads naturally to recommendations. So if you can search with a query, you can also search with an item or a document. And then there's a lot of other sort of downstream applications like entity resolution, which are actually special cases of search. So, is this thing, a duplicate of this other thing, or are these two things the same thing? And so we also see a lot of sort of content moderation, entity resolution, deduplication use cases around vector search. Lots of interesting stuff in terms of real-time personalization and conditional search. So not just having, sort of one embedding, for example, for everyone, but you can actually do conditional embeddings, which becomes really powerful in terms of being able to do real-time search and being able to steer it in a way which becomes much more powerful, and also results in a lot better with metrics and the sort of experience for users. And then there's things like classification as well. So zero-shot classification again is quite an interesting use case. So there's a whole host. Once you represent things as vectors, there's a lot of stuff that you can do. So I'll show you some examples of this, what it actually looks like vector search. Here's an example. This is looking at a whole bunch of sort of products, dog art. We get some dog art, but what's really great with vector search is just how powerful it is. So here we're doing filtering, but these aren't filters that are described by any kind of metadata. These are filters that you can just type in natural language and actually just start filtering the catalog. So vector search, doesn't require, it has much less requirements on what metadata is required, because it actually can learn the content of the data, and a lot of this stuff comes for free. So you can get these really powerful search experiences, out of the box once you've got really good high quality embeddings. So you can do, again, recommendations. So instead of searching with a query, here we've searched with a query, but we can look at actually now, we go into a product and you can actually look at recommended items. And again, depending on how you want to train your model, will depend on really what the sort of recommendations here look like. But you get a lot of this for free once you actually start the train. Again, high quality embedding models, you can start to do high quality search, high quality recommendations. and a host of other things. We can do a lot of conditional search in this real-time personalization. So here, this is the same backpack search, but you can actually condition it based on some context, really any other information that you have. And so you can see that they're both returning backpacks, but one is office themed, much more professional compared to say outdoor themed. And so you can imagine how powerful this is when you're doing it in real time, based on any kind of interactions or any other kind of priors that you have in terms of curating the search. And again, it all happens in real time. Basically it comes for free once you've got these high quality embedding models. And here's just another example. I think there's a whole host of things you can do in vector search around actual, moving away from just this sort of traditional search bar. What's really nice is that you can basically traverse the underlying kind of space, really easily. So, it becomes very powerful, to actually look at how things are related. How do you actually, do discovery across really large catalogs? And again, I think there's a whole, this kind of area is pretty much underexplored, and how do you actually bring a lot of this functionality to a practical UI, and how do you actually make it really work for users? So there's a whole host of really interesting things that come, just from having, really high quality embeddings with vector search. All right, so try to sort of set up a bit of background. So vector search, everything gets represented as vectors. It's really the embedding quality that sort of determines, how good everything downstream of that is. And so, even if you've got a really performant vector search system, you really need to have really performant models as well to really understand what you're doing. And so that's really what motivates what I'm going to talk about now, which is the generalized contrastive learning. So sort of taking existing methods for training embedding models and actually making them much, much more suited to basically, production search use cases. So I think, again, people are probably familiar with this. It's a really famous example of contrastive learning. So this was CLIP, came out in 2021, made famous by OpenAI, contrastive language image pre-training. And in this particular case, what it allowed was both, sort of text and images to live in the same vector space. And this means that you can now do multimodal search. You can query in text, you can get back images, you can query in text, you can get back text, you can query in images and get back images. And it's a very simple kind of problem setup. You have a whole host of captions on images, and then during training, what you're trying to do is match those captions, to the correct image. So really simple setup, requires, relatively straightforward data that can be collected, pretty easily, and becomes this really powerful technique. So, really simple, really powerful, and allows this cross-modal search. However, it doesn't, it sort of came about really as a pre-training technique. And so it wasn't necessarily geared towards, say, production search. And so there's a few things that aren't quite, that can be improved here when you're actually dealing with training models, for production search systems. So some of the current issues with, using a sort of simple clip-like pre-training are the following. And I should say that even though the previous example used, text and images, you can do images and images, you can do text and text. It's very sort of simple, method. It doesn't have to just be text and images. But so some of the big considerations are really that it's trained using these binary relationships. So it's just like a yes or no. This caption goes with that thing. This query goes with that document. But in the real world, we have much finer grained information, not just binary relationships. So there's no notion of ranking as well. So for a lot of queries, if you've got a one-to-one mapping for a query, there's only one answer, for example, but a lot of the time we end up with these degenerate queries where there might be many, many candidates. And so once you get to that point, not only do you want to return the relevant candidates, but you actually want to start to return them in a list, which is actually reflective of their importance. And this is something that doesn't really come for free. With traditional embedding models, you have to kind of work to get this in. And so we find that sort of re-ranking is not enough. So even in two-stage retrieval or end-stage retrieval systems, you want to have much better first-stage retrieval. And the other practical importance is that there's no real ability to use multiple pieces of data or information. So, a lot of these times for documents, you might have titles, you'll have abstracts, you might have different paragraphs, you might have metadata. At the moment, everything's just treated basically as the same. And so with product search, you might have images, you might have titles, descriptions, reviews. It's all these sort of other pieces of data which are related to a product or a document. But at the moment, embedding models just treat everything basically the same. And so we really want to be able to encode some of these relationships during training so that we can actually make use of all this data. And so here's an example. What I mean is, if it's a question and an answer, often there's a single answer. But if you're doing, say, product search or something very vague in terms of a vague head query, you'll have a lot of candidate solutions. And so what you actually want to do is start to produce them in an order that's reflective of their sort of importance. And so the kind of key thing that we want to do is not just define these relationships of what's relevant or not, but we actually want to start to encode, importance basically through the angle in this vector space. It's really high dimensional. And so not only do we want to put things in the same area, we actually want to encode their relevance, effectively as a part of a rank. As part of the angles. And so what we can do is take that sort of contrastive language image pre-training and start to generalize it. And so no longer do we have, sort of image to text or text to text or image to image. You can now have any combination of image and text to image and text, or audio or video. And so it's really generalizing how you actually do this and define these relationships between the data. But then you can also incorporate additional information, which isn't just about binary relationships for, say if a query is there related to a product, you can actually now encode different weightings for this. And so we get a lot of this information back from clicks, from add to cart rates, from any other kind of information, maybe relevance judges. And so now you can actually incorporate that into the training. And so it's very similar in the way that collaborative filtering works, where you have an item user interaction matrix and you try and factorize that. You can think of that very similar here. You're actually, instead of just having this diagonal in CLIP, you can actually have this user item interaction matrix, which you're trying to factorize through the relevant image encoders. And so this becomes much more flexible. So you can use many different pieces of data. You can actually start to encode these non-binary relationships. And you can also train directly for unified embeddings as well as multimodal embeddings, which becomes really powerful from a production standpoint. And so one of the key things in developing this sort of method was actually also developing a data set. So we're working a lot on these production systems on customers, we do a lot of private data. So we actually couldn't test these methods on publicly available data sets because they just didn't exist. And so we also developed a data set here. It's 10 million rows of product information across 100,000 unique queries, 100 results per query with ranking information, ends up being about 5 million unique products. And you can have a look at the GitHub there. That's where it's freely available to use. And what we also did was found in search systems, particularly, and the data sets was really lacking, was actually the splits that are related to production systems. So you might have a traditional trained dev test split, for a lot of machine learning classification problems, for example. But in search and recommendations, it actually is quite different. What you'll have is if you train a model on all of your known queries and all of your known data, then you actually, don't have anything that you haven't seen before, and that's sort of considered to be totally in domain. That's the training here. But then as time goes on, you'll start to see new queries. You'll add new documents that you haven't seen before. And so you start to move into these other regimes where you've got novel queries, novel documents. And if you let this go forever, you'd end up with everything being novel. And so in production, you don't just have, one part of this, you actually have a mix of this, and it will change over time. And so we really wanted to reflect, what we saw in production with this data set as well. And so the only piece that's missing from this now is this temporal component. So, but this, data sets like this have been incredibly useful for developing the techniques. And so what we do, if we actually train the models, on this data set, you can actually see these, these improvements, not just in the in-domain, which is where you've actually seen, the queries and the documents before, but also across new queries, new corpus, and then zero shot. And then of course the zero shot here is still relatively within the domain of say shopping and product search. It's not completely out of domain, but you see that it's significantly better than we've got a BM25 keyword search. So we've got some small amount of text metadata here, but not a whole lot. It's a very image heavy kind of problem. If we look at the pre-trained models, so these are ones that have been large-scale pre-training across sort of billions of samples. They do better in general than BM25, but are considerably lacking compared to actually fine-tuning using GCL on the data sets. And then if you actually if you do it just as a regular clip training, it comes out to be about half of what the GCL is. And so we also saw, we've been running this in production as well for quite a long time. We've seen significant improvements in the production A/B tests. And again, that actually came much before we had the sort of publicly available data sets to demonstrate that as well. But we've been using this in production. There's a whole, and a lot more other innovations that we can basically, still add in here. So there's a lot more to do And if you think about, where it's going in terms of multi-vector representations, I think it's pretty exciting. So I think one other aspect, which is really practical, and I think, there was quite a bit of talk about this earlier in the year. I think when OpenAI might have released, some of their embedding APIs, we could actually truncate the embeddings. And so what happens is, in vector search, basically the storage is proportional to the vector dimension, and your actual lookup time also related to the vector dimension, because you've got to do these calculations over each of the elements. And so there's a desire to reduce the storage cost, reduce the latency, while not really sort of having to compromise on any relevance. And so there's a couple of techniques here, Matryoshka representation learning and binary embeddings, which allow you to actually reduce the dimensionality of the vector, as well as reduce the precision of the vectors, so you can get much more affordable and performant search without having to sacrifice any relevance. And so what we can do, this is really about being production aware, like I mentioned. So in GCL at the start, by using many bits of data, we're actually able to become much more focused on what the actual end user is doing, much more production aware. We can continue that with the truncation of the embeddings. And so, like I mentioned, smaller embeddings are typically cheaper and faster, but often sacrifice relevance. Is there a way where you can make it cheaper and faster without sacrificing any relevance? This is where the Matryoshka representation learning comes in. So the idea is that you don't just train for one target embedding size, you actually train for multiple target embedding sizes. Again, really simple concept, really powerful, works, pretty much out of the box, a little bit of, hyperparameter tuning, but it means that when you train a model, you get a model that's performant, at some dimension D, you get a model that's performant at some other dimension, D on 2, D on 3, D on 4, and so on. And so that when you're actually at inference time, you can select, what kind of sized embedding you actually want to use. And if you, typically what we see is you can reduce it, 2 to 4x without really losing any kind of loss in fidelity. So in fact, some cases you can actually get slight improvements over the base dimensionality as well. And so here's just an example of that. So the green is the Matryoshka generalized contrastive learning. These are the results, on that previous data set that I showed. And so actually what we see is when we're at 512 is the original dimensionality here. What we see is that we actually improve results a little bit over the baseline. And then you can see as we truncate the dimensionality of the vector with the regular training that's in the blue, performance degrades, pretty reliably. But with the sort of, truncation aware training, the Matryoshka representation learning in green, we're able to preserve the performance across these dimensionalities. So you can reduce the dimensionality here by a factor of 4 while retaining, something like 95% of the performance. And so that means you can, literally reduce your storage costs due to the vectors by a factor of 4 with only a really minimal loss in, in sort of relevance. And so there's another theme very similar to that. So instead of, reducing the dimension of the vector, you can sort of reduce the bit depth. And so, the furthest you can go there is, binary embeddings. And so you allow, instead of storing them as, full precision or half precision floats, you can, store them as binary, ones and zeros. And so you just quantize, the embedding. The thing is, if you just, take a normal, sort of regular model and, binarize, you'll get really bad performance. And so what you want to do, just like if you just naively truncate your embeddings, what you want to do is actually learn how to binarize during training. There's a few different flavors and there's some nuance to how you can do it. The issue with, you can see one issue with binary embeddings is if you've got a D-dimensional vector and it only can, differ in sort of D places, your actual output space, the score space becomes really heavily quantized. And so everything kind of maps to the same value. And so there's a few different tricks that you can play to basically help with that in terms of your actual sort of scoring. Here's some examples. So the blue is full precision float, and then we've got mixed precision and then binary in the green, the dark green. So we can see that we lose a bit more in terms of relevance compared to the Matryoshka learning, but are still able to preserve quite a lot of it. The thing here is that it ends up being, pretty much a 32x reduction in storage cost here. So it's a huge reduction. And again, I think there's probably ways that you could actually preserve all of the relevance here, by going to even larger, embeddings, for example. A 32 reduction in storage allows you to probably, take up another factor of 2 or 4 somewhere else to retain all of that relevance. All right, so I'll just finish up here. So conclusions, typical embedding training is not really generally optimized for search, like I mentioned. So there's a few things that are missing. Being able to use all of the data that you have about a document or about a product. We want to encode more than just this binary relationship. We want to encode this notion of rank, so not just return relevant things, but return relevant things, ordered by importance. We can optimize directly for the production and the business use cases. So I guess one thing I failed to mention was this notion of rank can come from all these business objectives. So add to cart rate, revenue, whatever you care about, you can actually bake that now in to this model training. And then you can use it to have lower resources in production, lower inference costs, lower storage costs, like I mentioned, through this truncation and this binarization. And yeah, I'll put a few links up here. There's lots of blog posts, a couple of papers. Check it out. Marqo links are also there. Yeah, I'll leave it there. Thank you.
Thanks a lot, Jesse. I also put a bunch of the resources I found online on the Zoom chat as well.
Awesome.
Just for folks to check it out. Yeah, so let's spend maybe like 3 or 4 minutes for Q&A. If there's any real-time question from the audience. So I have one for myself, which is, for the construction of the GCL, not GCL, sorry, the 10 million Google Shopping dataset. Can you talk more about the data collection process? Like, how did you and your team collate and construct that dataset?
Yeah, it's a good question. I think the dataset, there's a big, we have a big issue actually trying to get representative datasets. So what we ended up doing here, we had to create the queries. So one problem is getting representative queries. So each business domain will actually have quite different query distribution. So that's one challenge. So we ended up developing, basically from a taxonomy, what the queries would be. So using ChatGPT to help build out 100,000 queries from an existing taxonomy. So that gives us the queries. And then we used Google Shopping API basically to get back, from something that, a sort of oracle in terms of what good search would be like. So we treat that as an oracle and then use those results and the rankings from Google's shopping as the notions of rank and use that back as a way. I mean, if anyone's listening and has, data sets or any data they want to contribute to this domain, definitely get in touch because, representative data sets here are really hard to come by. And so, and there's a huge variation. And I mean, things like the query coverage is really important for downstream performance.
Got it.
And one quick question from my end. How do you do for multimodal embeddings? Like, for instance, and I'll talk about it more during my presentation, but we have a big, thing with having audio plus video plus text embeddings and making work in the same, format, etc. And we typically use some sort of image bind and have some proprietary blocks around that. But yeah, curious to know how you do it, for instance.
Yeah, that's right. So it's incredibly flexible. So yeah, we've done other ones with audio, for example. And so the whole point is that, in that first image with clip, you've got a text and an image, but you can have any number of encoders going to the same thing. So you can have paired data, you can have triplets, whatever you want. Again, super flexible in terms of how, you train it. You can also do, sort of modality to modality. I mean, it's pretty composable. So I think there's no real tricks other than, just if you've got the data, put an encoder in. If you've got some pairs, do it, run some hyperparameter tuning. Yeah, things like image bind. There's a few other ones. I can't remember off the top of my head, but yeah, we've, again, just have the encoder, train the embeddings. That's about it.
Yeah, definitely. Thanks.
Yep. And then there's also one question from Brian on the chat. He asks, could there be any challenges in using GCL on smaller datasets?
Yeah, I guess it depends how small. I think it's generally applicable as far as we've been able to see. the key thing with the contrastive learning is that you need to adjust your batch size relative to basically the sort of data set. That's one of the tricky bits right now, because yeah, you've got this sort of in the naive implementations, you've got everything's treated as an in-batch negative. But if you've got actual false negatives, which things that shouldn't be considered to be false negatives, then you can actually really hurt performance. And so you either need to adjust your loss function, or you need to adjust your batch construction and sampling to accommodate that, or you can just lower your batch size until it's something small enough that this becomes less of an issue. So it's totally possible, but just reduce the batch size basically.
Yep, I hope that answers your question. Awesome. Well, thanks a lot, Jesse. And I know that Marqo, the company, also doing a lot of interesting work in this space. I actually been following your newsletter, and I know you guys been putting out like a online courses, right? Which is on what is it? Fine tuning embedding models for semantic search. So yeah, if you put that on the chart for audience, to check it out afterwards.
Yep.
Yep.
Perfect. Thanks.
Yep. With that in mind, yeah, Alex, do you wanna go ahead, get started with your side?
Yeah, definitely. Let me share my screen. I'm gonna have to hop in between different share screens, but it's fine.
Nice.
Yeah, so basically, great to be here today as well, everyone. And yeah, we're working on audio models, and so to us, it's important to understand, to really see from understanding to audio, basically, and how 12 Labs and Adorno can transform video production. So before really starting and talking about anything about the company, I just wanted you to understand what is the power of audio, especially in video production. Most people always think about video first, but it's often going to be 50-50 in terms of importance between audio and between sound. And so we've actually taking an excerpt from Dune, we removed completely the audio and use our models to automatically put back some sound design on it. So sound design as in sound effects, ambiances, and music. So I'll just play this and then I'll start the presentation. All right, back to the presentation. So I hope you've seen that sound is relatively important, because without it, it wouldn't have made any sense, and you wouldn't have felt anything as well. So I'll give a much higher level view presentations. There are some technical things at the end, but just so that you realize, so post-production is essential, but it is extremely slow. It requires 3 to 6 times as much time in post-production as just production time. And a single minute of audio for a movie like Dune that you've just seen can take up to 4 hours to produce. So there's that, and it's extremely fragmented. There are usually 4 to 5 applications within the post-production workflow, even in audio, and there are so many formats today that are needed for different creators, and that they have to adapt their content for. And not only that, it's also extremely technical. Adobe says that there's a need for over 100 hours to kind of master Premiere Pro, and most companies tend to outsource anything that's related to content creation because they don't have simple tools, because it takes too much time, and they don't have anyone that's really good enough for that in-house. And the idea right now, the way we're really starting this larger vision is to see, well, can we make sound design as easy as just using Canva, for instance? And the reason behind that is that if you look at today, the multimodality in the creative AI landscape is still kind of fragmented. So you'll often have, if you have to create a movie, if you have to create a video or something like that, start with text models to generate the script and to give you some ideas. So you have ChatGPT, Gemini, Anthropic, etc. Then from this text, you can generate images, which can give you inspiration from Midjourney to DALL-E, and then you'll have to use those to feed them into the video generation models. So Runway, Luma recently, and Pika. But then when you get to audio, you cannot use anymore the video or the image or whatnot. You have to use texts. So whether it's for the music with Suno or Udio, voices with 11 Labs, and now they also have sound effects. And it's very text-based. And so there's there's a removal of this huge amount of data that is available within the video itself. And that's something that we're working basically towards having video to audio models. The reason behind that is that we want to be this accessible one-stop shop. And instead of creators having to go through, open 3 or 4 Chrome tabs and listen to all the possible different sound effects and music, etc., do the research and then do the downloading, the importing, the editing of the sounds, checking for royalties, etc. With video to audio models, now all of this is something from the past. And all that pitch sounds very salesy, but I'm going to just show you a demo basically of how we have this new way to perform sound design and how we really leverage both video analysis as well as a sort of co-pilot for the user in order to have something that's much more refined. So I'll just share my screen, this one. Okay. So the way it works is we have this very similar but very simplified video editor, which is focused constantly and primarily on sound. So once you're in the editor, you can simply create a ribbon. And by creating a ribbon and clicking on enter, we're sending to our models basically this small portion of video, and it's analyzing the video. We have some video models behind that do video understanding. They understand the context, the people in the scene, the objects, emotions, etc. It gives us suggestions for that specific portion of video that's been selected. And then based on that portion, it also generates them based on the video. So it mixes it directly in place. And I'll talk about this a little bit later on how we do it on the model side. But basically, if someone is moving from the right to the left of the screen, we're able to pan the sound from the right earbud to the left earbud. And we're really using the video understanding to completely modify the soundscape of the video. And we do this with sound effects. We can also generate voices on this the platform as well. And we also do it for music. And once again, similarly, we first analyze the video, which generates a text prompt suggestion for the user, and then the text prompt suggestion, which can be changed. And based on the text prompt as well as the video, we're able to generate a music that really matches what's going on in the scene. Okay, and I swear this is my last change of screens. We'll finish on the presentation here. So this is basically how we see sound design and production really evolved in the next weeks, months, years. In terms of technicality, so how we do it is that we use the video as well as a user input text, but the text is not always necessary. And on the video side, we do object detection and video captioning. So the idea here is to really extract as much detail as possible about the scene with object, actions, context, etc. And those, like by analyzing the scene, we're able to make the audio suggestions that I showed you just earlier on the platform. With these audio suggestion, the user is able to take that and select the suggestion, and we re-leverage the video afterwards to condition our models in order to generate the audio as well as the music. Once this is done, we do have some upsampling methods in order to increase the quality of the audio to 44.1 kilohertz, which is basically industry standard for what good audio is considered to be. And then we have more audio mixing models, and I'm going to get into them because it's probably one of the interesting things. So in terms of video understanding, how it works is that the user inputs their initial video. Based on that video, we split it into different scenes with some video models. We really understand where to cut and where different scenes should be. And within each scene, we have two different classification models. So one is for sound effects. So sound effects are for things in movement, people, animals, taking your bottle and smashing it on a table, and really impact sounds. And then we have the ambiances. Ambiances are more contextual, so they will be here a cityscape, for instance, birds chirping, city sounds, and whatnot. Then we are using the motion as well of the video. So for instance, the image on the bottom right is taken from the paper code tracker from Meta. And we're leveraging, so we don't use, well, we've used code tracker initially. The model is very big, so we don't use it in production, and we have our own. But by taking the label of the detected object person, we can relate it to a sound. And then by using this, we're basically able to modify the audio. And how that works is, for instance, we can use the residual maps of the ResNet, and here on the bottom right, this is a grad cam, and we're able to calculate, for instance, the barycenter, which is the center of this heat map, of this activation map, and by seeing the coordinates of how it moves, we can very easily pan the audio. So by the barycenter going from the right of the frame to the left of the frame, we pan it between the earbuds. And the same goes for if the area of this activation map increases or decreases, we can increase or decrease the gain of the audio. And we have plenty of other similar methods. We're really mixing between having some heuristics, which to us can be important in some ways. We tried to automate everything with models initially, like pure machine learning models. And those were very, very heavy. And some heuristics like using this barycenter and area of the activation map actually works really, really well. And yeah, it allows us to sync the audio very well with the frames. And then we have some proprietary blocks as well there. And yeah, and to finish off, so I'll be much shorter, but there's a lot of use cases that we think are foreseeable with using 12 Labs and Adorno, video understanding and audio generation. For instance, it could be really easy to do some sport highlight reels, finding the right moments with video understanding with 12 Labs, and then upscaling that with some custom audio, which would be people cheering for the sound effects or custom music. Same goes for the video game cutscene audio augmentation. We've actually been working with a few people that use our products, especially for video games, because it's content that doesn't inherently have audio on it. And not only that, but video games as well, not just a cutscene, are dynamic. And our technology really caters for dynamic movement because we take it into account. So if you're shooting a gun, whether it's a gun in an open space or a closed space, whether there could be reverberation or echo, our models take that into account. And so we've been integrating that into video games as well. And yeah, we can see it as far as maybe going to virtual reality experiences and whatnot. So we do believe that the possibilities are endless. Our initial thing is really going into this audio side of things. There is no reason afterwards to not continue developing it for further purposes. But right now, it is sound effects, ambiances, music, and we've got some speech generation as well into it.
Great. Well, thanks, Alex. Thanks. Appreciate your short and sweet, presentation. A really cool demo. And it's explaining the workflow, how it works, the toolchain, as well as potential use cases between Adorno and 12 Labs. And yeah, I'm excited to discuss some of those use cases for some of the future engagement and how we can create interesting tutorials or demos, right, with our two platforms. Yeah, with that, we still have roughly 10 minutes left on our call. So So any question for Alex about, I don't know, the technology and anything you want to discuss?
Yeah, I actually have one question. So first of all, thanks, Alex, for presenting. Like going back to your initial example with the dune scene, so how, like in that case, like the audio was very specific to the movement of the beacon. So how Adorno ensured that there is like the audio and the video are synchronized, or like even when you mentioned the like firing a gun, obviously the action and the sound, it's important that they are aligned. So I'm curious to know more about that aspect.
Yeah. So basically what we do is so in the demo you saw that I highlighted a small ribbon, like I can create a small ribbon on the editor. So we take this, we transform it into a video embedding, and then we create the textual embeddings based out of this. It allows us, we create suggestions from that. And once we've generated the audio, so let's say that the suggestion here was like the beat thumping on the sand, right? On the, I don't know how you call it. We can generate some sort of audio for that. And then we're going to see how we can sync it and like mix it correctly in place. And for those models, so as we said, so yeah, the sound isn't generated perfectly for it from the get-go. It's like generated for what it sees, and then we have other models to sync it and mix it correctly. To sync it, we really use the movement. So we have, as I said, some models with activation maps from ResNets, and we have other models that are much more like there's a lot of heuristics in it, but we really synchronize the moment we find the velocity of the two different parts moving, and when we see it's maxed out, we sync it from that point onwards. And then we take the distance, like we've used SAM and Dino V2, and we use the distance in order to scale the gain of the audio.
Okay, interesting. And what about the inference time? Like, is it something like if I want to iterate fast, is it something possible? It takes quite a while to.
Oh, it's actually quite quick because so the method that we use to generate is, I'm not sure like everybody uses that way, and it's why the vector search was very interesting because we also use a lot of vector search in what we do. So for our audio, we have a very, very big data set basically. And by taking in the video embedding plus, so we use image binds and other models, and we have embeddings for all our audio. We have the embedding for the piece of the video, and we have an embedding for the text as well. And so we're able to use the video embedding plus the text embedding to find a subset of the most relevant audio embeddings. And then we condition our models, our generation models, with this subset of audio embeddings that make sense, which means that we can have very small audio generation models and makes the inference time very small. Yeah, usually to generate using like 4 suggestions, and there are 4 sounds per suggestion, so 16 sounds, it won't take you more than 30 seconds.
Oh, wow. That's cool. Well, congratulations.
I had a question as well. I guess it's 2 parts. One is like, do you see any, I guess, issues with the sort of the length that models can reason over, or it's sort of applicable to? So obviously, like an hour-long clip is probably not going to be possible to sort of match to it, but it's going to be, segmented, I guess. But I guess as well, everything's sort of cut up naturally into scenes, and so maybe that length is right. So that's the first sort of question. And then I guess the second question is, do you see any issues with like in versus out of domain for being able to match, audio, video, these kind of things?
So the first question being like about the length of the.
Yep.
Yeah, so
Length.
right now that is one of the limitations. We have a maximum length of 5 minutes audio that you can put in the platform. But the thing is, if you want to have 5 minutes and 5 minutes and 5 minutes and 5 minutes, we do try to find a method in which to, glue the two clips longer, which isn't too much of a problem when it comes to sound effects, because usually they won't be too long, and if it's ambiances, they can be somewhat repeated, then modified a bit, and you won't see too much of a difference. For music, it is kind of a pain. But yeah, right now we can generate 3 minutes and 30 seconds of music about at a maximum, which for our users has been far enough. So that's first question. And sorry, second question was.
Inverse is out of domain in terms of, just like the content basically across all the modalities. Because,
Oh, yeah.
there'll be, obviously it's not going to, but maybe that's not an issue.
Right now, it's not an issue, which is surprising. Yeah, we found it to really correctly have all those contents and all those modalities and talk to one another, talk to them like in a good way. The image bind has been really, really useful in order to really like make sure that our audio and our video and our text embeddings are the same. So that has been very useful. If I'm answering the question correctly.
Yeah.
But yeah, the multimodality hasn't been too big of a problem. Uh, I would say that something we were doing initially, which was more problematic, was really trying to basically brute force the audio mixing and doing no heuristics. And we had models that work, and they work really well, but they would take an absurd amount of time. And yeah, I'd say as a word of end, in a world where like everyone's like focused on AI and solving everything with AI, and everything has to be fully AI. Having a bit of heuristics, it doesn't hurt, and it has, we've used those heuristics in our vector search for the audio generation, and it's like the quality has been like tenfold, and the inference time has been tenfold as well, tenfold, I mean, like enhancements. And same for the mixing. Like the little heuristics that we've been able to implement within the audio mixing has made it so much faster that yeah, I'd say that was really useful.
Awesome, thanks.
Great. Okay, it's a technical question here on the chat. Is it possible now? Do you have plans to implement customization of results, like shifting to different style as when using a LoRa with Stable Diffusion?
Yeah, it's a great question. So right now it's not possible. We are thinking about implementing such things in the platform, especially being able to, well, allowing users to use their own LoRa's, or having some sort of like node editor to really be able to swap models around and swap things around. We do have a lot of proprietary models, so the audio generation is fully proprietary. We're not at all using stable, even stable audio in it. And so right now, yeah, we're focused on our proprietary side of things, but we want to open up and allow people to use some of what they're doing as well and doing style transfer. So yes, it will come at some point.
Great. So is Adorno product available for usage? Anyone can set up and try it out, right?
Please do. Right now we're still free. So yeah, it's completely available. Go to Adorno AI, create an account and enjoy it.
Great. Yeah, super excited to hear that. Yeah, excited to try that out soon. Okay. We have 1 minute left. Well, actually, it's 2:30. So I think, yeah, we can conclude the webinar now. Thanks both the audience, both the speakers for taking time today and give very interesting technical talks about vector search, contrastive learning, as well as multimodal models for from video understanding to audio generation. Thanks to the audience for engaging and asking good question. The recording of the session could be available within 2 weeks, and be sure to highlight that on YouTube and share it to speakers so they can share it with the audience. And yeah, we run this webinar series on a weekly basis, so stay tuned, and I hope you see many of you in the upcoming session. with that, yeah, thanks for making time today, and hope you guys enjoy the rest of your weekend. Bye-bye.
Thanks, everyone.
Thanks. Have a nice weekend.
Yeah.
Bye.
Bye, guys.